Let's try to find the subgame perfect equilibria of the game. There are 3 subgames in total. This one, and this one. The third subgame is the entire game. Subgame perfect equilibrium is a strategy profile in which every player takes a Nash equilibrium action of each subgame in each information set. Consider a subgame that starts at the information set H2L. The best response of player 2 is to choose R. Now, in the subgame that starts at the information set H2R, the best response of player 2 is to choose L. Given that these best responses of player 2, consider the subgame that starts at the information set H1. The best response of player 1 in this subgame is to choose R, given the strategy profile of player 2, because player 1 knows that player 2 will choose R if player 1 chooses L, while player 2 will choose L if player 1 chooses R. Comparing the payoff of player 1 in these two scenarios tells us that player 1 is better off choosing R. This way of deriving subgame perfect equilibrium is called backward induction. And as a result of backward induction, we find that player 2 takes action R at H2L and takes action L at H2R. And player 1 takes action R at H1 in the subgame perfect equilibrium of the game. When you describe subgame perfect equilibrium, please do not simply write down actions that players choose. You also need to describe what player 2 would do if player 1 deviates to action L. This is because action R would not be the best response of player 1 if player 2 chooses action L when player 1 deviates to action L. That is, the best response of player 1 depends on the entire strategy of player 2. You need to write down the complete plan of actions to determine subgame perfect equilibrium. The backward induction in the previous slide shows that player 1 does not have an incentive to deviate to action L given the subgame perfect equilibrium strategy of player 2. We also checked that player 2 has no incentive to deviate to strategy LL and strategy RR, given that player 1's strategy is R. What we have not checked is player 2's deviation to strategy LR, where player 2's strategy is changed at both information sets simultaneously. It turns out that we do not need to check such deviation due to one-shot deviation principle. This principle claims that we only need to check deviations at a single information set to check if a given strategy profile is a subgame perfect equilibrium. This principle saves a lot of work to verify subgame perfect equilibrium because otherwise there could be a large number of deviations to consider in a more complicated game. We will see how useful this principle is when we get to repeated games. Now, let's go back to example 1 we saw at the beginning of this tutorial. Recall that accept bomb and reject not bomb are the two Nash equilibria of the game. Accept bomb is, however, not a subgame perfect equilibrium of the extensive form game because player 2 chooses not to bomb in the subgame starting at player 2's information set. You can easily see this if you apply backward induction. Given player 2's strategy, player 1 never accepts player 2's demand, since player 1 knows that player 2 will not blow up the bank in the end. Now, let us consider an example of ultimatum game. In this game, player 1 first chooses offer x, which is a number between 0 and v, where v is some positive constant. Then player 2, who observes x, decides whether to accept or reject the offer made by player 1. The payoff for player 1 is v minus x, and the payoff for player 2 is just x, if player 2 accepts the offer. And both players receive nothing if player 2 rejects the offer. It is not possible to draw all the information sets of player 2 here because there are infinitely many of them. And the graph on the slide here is a rough picture of what is going on in this. Let's find the subgame perfect equilibria of the game by backward induction. We first derive the best response correspondence of player 2 at every information set, in which an information set is given by the value of x. Since player 2 gets nothing if she does not accept player 1's offer, player 2 will always accept the offer x as long as it is positive. Now, player 2 is indifferent between accepting the offer and rejecting it when x is 0, because player 2 gets nothing anyways. Given the best response of player 2, what is player 1's best response? Player 1 will not offer a positive amount of x, since he can always find a smaller value of x where player 2 still accepts the offer. And so player 1 will not offer any positive x in the subgame perfect equilibrium. When player 1 offers nothing, however, player 2 can be either accepting or rejecting the offer. What does player 2 chooses in a subgame perfect equilibrium? It turns out that player 2 has to accept the offer of x equals 0 in a subgame perfect equilibrium, because if player 2 rejects the offer, then player 1 gets nothing, and player 1 can deviate to offer positive x to increase his payoff. Therefore, player 1 offers nothing, and player 2 accepts any offer amount x is the unique subgame perfect equilibrium of the ultimatum game. Note that the strategy profile of player 2 in this game needs to describe what player 2 would do when player 1 chooses some positive offer amount x as well. This means that player 2's strategy is not just accept. Player 2's strategy is accept any x between 0 and v. This way, we can see what player 2 would do if player 1 offered some positive amount of x.